Welcome to the Quantum Detectors webinar. It is great to see so many people connecting from around the world. Our guest speaker today is Dr. Leifeng Liu. Leifeng obtained his PhD from Stockholm University in microstructure characterization of novel materials using advanced transmission electron microscopy. He is now the CEO of ReadCrystal Biotech, a company based in Suzhou in China. They specialize in electron diffraction and provide commercial services to users around the world. ReadCrystal are using quantum detectors MerlinEM Quad, a direct electron detector, on their gel microscope for electron crystallography. Leifeng will present an overview of electron diffraction tomography, 3D ED, micro-ED methods, its applications, and will highlight interesting projects they have been working on. During the webinar, please ask questions in the chat box. We will endeavor to answer these at the end. This webinar will be recorded and it will be available to watch again through our website. Everyone who has signed up to the webinar will also receive a link by email shortly. And with this, I would like to introduce our Merlin detector. Before I hand over to Leifeng, let me briefly introduce its applications. So first of all, Merlin is a hybrid pixel electron detector based on the MEDIPIX technology developed at CERN. The detector is an application-focused system. We supply live 4D STEM capabilities together with versatile and controllable readout system. We install on microscopes of all major vendors, and we have developed a robust interlock system, which lets us install MerlinEM opposite a third-party camera. And the key ability of MerlinEM is that the electrons are counted by advanced analog to digital circuitry in each pixel. This means that any subsequent process is digitized, which has advantageous implications, because energy deposited by each electron is recognized against user-definable threshold, and the electron is only counted if enough energy has been deposited. This suppresses many sources of noise, from background electronic and thermal noise, blooming to readout noise, which is key for low-dose imaging. Unlike previous generations of cameras, such as CCDs, the MEDIPIX technology enables us fast frame rates and precise detection of single electron events. So MerlinEM is a versatile detector, which is routinely used for advanced 4D STEM and electron diffraction research. It is successfully applied to study material properties and dynamics. Merlin is popular across many disciplines, in physical sciences and in material sciences. It's especially in energy storage, solar cells, printable solar cell materials, or defect analysis. In life sciences, people study biomaterials or structures of viruses or biofilaments. Advanced STEM imaging is a method of choice in semiconductor interface studies, like shown here in metal oxide semiconductor devices at the top left, or in magnetic nanocrystalline materials at the bottom left. Scanned diffraction is used to analyze various materials, for example, in emerging memory technologies in the middle top left panel, or in solar cells to visualize grain boundaries or nanocrystal interfaces in the top middle right as well. There are similar varied applications of Merlin in electron diffraction tomography, 3D ED, micro-ED, which is the topic of today's webinar. It is a method of choice in studying metal organic frameworks, as shown here at the bottom in the middle, or Covalent Organic Frameworks. These frameworks are of great commercial interest, as they are the future of catalysis, of gas storage, or gas vapor separation technologies. They are widely used in biomedical imaging as well, and in luminescence. All those techniques and imaging modes are supported by Merlin software, as you have been demonstrated in the top panel. Here in the software solutions, when we can see the magnetic material being imaged, or at the bottom where experiments are being imaged in the TEM mode. This software we offer with MerlinEM is a very user-friendly interface that enables users to customize the experiments. There are also more advanced options using scripting, which are enabled for Merlin as well. And let me tell you why Merlin's versatile readout is extremely useful for direct applications in different methodologies. It enables detection of single electrons and up to 4 high-dose diffraction patterns. Merlin provides very high frame rates, which depend on the bit depth used. And the cross-section of the 24-bit diffraction pattern on the right shows the high dynamic range of the Merlin readout with 6 orders of magnitude range. So high dynamic range together with extreme beam hardiness are key for diffraction experiments. In this case, a very beam-sensitive sample of a solar cell material was imaged at 300 kilo-electron volts in scanned diffraction geometry with parallel or close to parallel beam. Please note the wide dynamic range of Merlin. Image on the left shows the linear scale, and we only see the central diffraction spot. On the right, in logarithmic scale, the complex diffraction pattern with spots of low intensity is clearly visible. Beam stopper is also not required, which maximizes the amount of information present in the data. And results like this can only be obtained thanks to the high speed and sensitivity of the detector. And let me briefly discuss differences in electron diffraction modes. Firstly, we can choose convergent beam diffraction, as shown in the very furthest left panel, or combine it with a small angle beam tilt to perform precession electron diffraction. Another experimental option is a nanobeam diffraction, which utilizes a small nanometer-sized parallel beam. After the beam is transmitted through the sample, the diffraction pattern is in the far field detected by a pixelated detector. This method is very dose efficient and enables collecting information from very beam sensitive samples. Therefore, it's the method of choice in scanning diffraction and electron diffraction tomography, 3D-ED, micro-ED. In this setup, the sample is tilted, which enables collecting different diffraction patterns at several angles. This in turn allows for the 3-dimensional reconstruction of the structure of the material. For many samples, it is essential to work under very low dose conditions to prevent beam damage. And let me introduce the implementation for MerlinEM with serial EM software. It is widely used in life sciences because it offers versatile experiment options, including fully automated data acquisition. The work was done in collaboration with our colleagues from the Hexi beamline at Diamond Light Source in the UK, Pedro Nunes and Alistair Seabird. We take advantage of full benefits of serial EM for 3D-ED or micro-ED. The movie has shown you examples of how electron diffraction tilt series are collected with serial EM on Merlin. Please note how the high dynamic range of the detector makes a massive difference in detecting very low intensity spots. This is a continuous tilt series with 100 millisecond frame exposure rate and very low dose beam settings. There is 0 dead time between frames in the movie. We overcome the latency in serial EM software by a custom design of the plugin. And these experiments are only possible thanks to the use of direct detection technology, which enables recording movies from the continuous rotation experiments. And let me highlight again how crucial the detector sensitivity and speed are for electron diffraction. Here is an example frame of the 3D-ED on Azel light collected by Pedro. I marked the 5 rows of diffraction spots to show how MerlinEM enables detection of very low and very high signal intensities simultaneously. Merlin can withstand a direct diffraction beam even at 300 kilo-electron volts and still detect the diffraction spots very close to the center without any damage or detrimental impact on the data quality. It gives a huge advantage over technologies which require a beam stopper, where this part of the signal is lost. Moreover, we can detect electrons across the range of 6 orders of magnitude in each pixel in 24-bit mode. The panel on the left shows the cross-section profiles of the intensities shown in the middle image. Using Merlin's logarithmic scale is the key to this application. Importantly, on the right, you can see how far the diffraction resolution can be pushed with Merlin, with 0.63 angstrom ring visible. The data processing is being done using Dial's software package, which is fully compatible with MerlinEM data. This makes Merlin an ideal tool for small molecule electron diffraction and other applications on sensitive materials. If you are interested in using MerlinEM detector with serial EM, you would need a plugin package, which we make available for our customers. For more information, write a message in the chat box or contact me directly by email. I'm happy to answer any questions and help you set up your experimental workflows. And let me also introduce another automation option for electron diffraction with MerlinEM. Instamatic software will be available soon. You can now download the beta version from GitHub using the link provided. Please contact me if you have any questions regarding this implementation. Both serial EM and Instamatic interfaces and plugins for both softwares are available for free. Do contact us so we can help you build and optimize your workflows. And I would like to say that there is a vibrant community of Merlin users around the world. There are over 70 Merlins installed in more than 15 countries. I mentioned a few research highlights, but there are many more. Over 70 publications in high-end journals have been published so far. And with this short introduction, I would like to hand over to Leifeng from ReadCrystal Biotech.
First of all, I would like to thank Covalent Detector and Adriana for hosting this event to let us have the chance to present our result to the audience all over the world. I'm from ReadCrystal Technology. I'm the CEO and founder of the company. My name is Leifeng Liu. The talk I'm going to give today is about the application of micro-LED in the development of novel drugs and novel materials. And the ReadCrystal Technology is a company providing a structural solution for researchers in pharmaceutical industry and in material research. First of all, I would like to introduce the technology background. In the past 100 years, the majority of the structures were determined by single crystal X-ray diffraction. This technology has been serving human beings for a long time and contributed a lot to our understanding to the world. But there is a severe disadvantage for this technology. The basic one is that by using this method, we have to grow a crystal big enough in order to get diffraction patterns with considerable intensity. So normally, for small molecule, several micrometers, crystals in the size of several 5 micrometers is minimum, and for protein sample, even larger crystal is needed in order to get a good signal from the diffraction pattern. So because of this, it takes really in many cases, it takes very long time to grow to get structure because we have to grow a crystal big enough, especially in the structural biology. It might take a researcher several months to several years to grow a crystal big enough for diffraction. And in some case, due to the property of the molecule of the protein, we may fail to grow a crystal big enough for the diffraction. So for those samples, the structure might still be unknown, and moreover, large quantity of sample is needed to perform to test different crystallization conditions in structural biology, maybe like a few hundred or even tens of hundreds of experiments has to be done in order to find a suitable crystallization condition. So this means a large amount of sample is needed. Hundreds, maybe hundreds of milligrams of sample is needed, and those protein is quite precious. It's the same in small molecule, especially in pharmaceutical industry. In the early stage of drug discovery, all the molecules are synthesized in the lab by organic chemistry. Maybe it takes 10 steps or even more steps to synthesize the molecule. So hundreds of milligrams of sample can cost a really lot for the scientist. There are basically two approaches that we can think about to overcome the disadvantage of the single crystal XRD. First of all, we can make the beam stronger. So scientists have already built many synchrotron light sources around the world in order to have a stronger, a brighter X-ray beam. But the price of this facility is quite expensive, and it can significantly reduce the size of crystal, but still there is a limitation. For small molecule, you still need a crystal size of around 5 micrometer, and for protein, you need a crystal size around 50 micrometer, even in the synchrotron light source. The other approach is to change the radiation source to switch from X-ray beam to electron beam. So micro-LED was invented from this follow this source. Electron diffraction can be collected on transmission electron microscope. The price of the instrument is much lower than synchrotron facility. The price is around a normal lower end TEM cost only like $1 million. But with this instrument, we can already solve the structure of crystals as small as 100 nanometer, much smaller than the crystal solved in synchrotron by using synchrotron light source. So the basic theory behind this is electron interact with matter much stronger comparing to photon. So you only a very teeny crystal is needed to generate diffraction patterns strong enough with enough information for us to solve the structure. So since it was invented, the method was invented, it has already attracted a lot of attention from both academia and the industry. We can see the publication related to this method has grew dramatically in recent years, and it's also ranked the top 10 scientific breakthrough of the year 2018 by Science magazine. So the workflow of micro-LED is quite straightforward. You just take a powder sample, crystalline. It has to be crystalline. So normally, before we put sample into microscope, we use powder X-ray diffractometer to check the crystallinity of the sample. If the crystallinity is okay, then we can just simply disperse the powder sample onto the TM grid and then insert grid into the microscope. This is this is an nano crystal in the TEM, which you often see after during the measurement. Then you can select the crystal and collect data from this single crystal. Here is the diffraction pattern collected from the crystal. Then the next step is to convert the series of diffraction pattern into a three-dimensional diffraction pattern. Then with this three-dimensional diffraction pattern, then you can solve the structure directly by using, for example, direct method. So the advantage for micro-LED is that we can solve crystal structure from nano-sized crystal, powder crystal, and needle-like crystal, and we can even solve nanocrystals from a mixed phase sample. And because we skipped the crystal growth step, so we saved a lot of sample, so it decreased the sample consumption in total, and we can also significantly reduce the time for determining the structure, because we skipped the step which cost most time. Micro-LED technology can be applied to different research fields. For example, it can solve the structure of new materials, MOF, COF, zeolite, small organic molecules. It can also be applied in the field of drug solid-state research for soft crystal structures or polymorphs of pharmaceutical compounds. It can also be applied to structural biology to solve structure of proteins. ReadCrystal is a company working on providing one-step solution for structural analysis. We provide a service for micro-LED, single crystal X-ray diffraction, as well as cryo-EM. At present, we have more than 50 people in the company, and provided service to more than 100 customers. This is our lab in Suzhou. We have purchased our own transmission electron microscope. This microscope is optimized for micro-LED application, and I think so far it's the only one in China that the only TEM in China that works only for micro-LED. So all the accessories, all the workflow is optimized for micro-LED application. We have also a biology lab, crystallization lab, to prepare the protein sample and to crystallize the protein and the small molecules. So we work on three fields, as mentioned. Structural biology, we can provide protein expression, purification, crystallization, and collect micro-LED as well as X-ray diffraction data. And we also provide cryo-EM SPA service to determine mostly membrane protein structure. For drug solid-state research, we provide polymorph screening, structure determination, and we also provide service to solve structures of new materials. Next, I'm going to give several examples of our work. The first one will be in metal organic frameworks. All of those examples are done either by our company or by the founders of our company. This is a metal organic framework with nickel metal as the node, and by carboxylate organic linker. So the structure of this MOF is solved by using micro-LED method straightforwardly from a crystal in the size of around 200 nanometer. And we can see the simulated diffraction pattern from the solved structure is quite consistent with the experimental diffraction pattern from the sample. And the second example is covalent organic framework. This kind of material is meant to be more stable than metal organic framework. But one big issue for this material is that it doesn't like to grow into a large crystal. So determining the structure of this kind of material is always a headache for scientists, because for crystallization you need a reversible reaction, but covalent bond doesn't. It's not like very reversible. So in this case, we collect the data from a nano-sized COF crystal, and the diffraction. We got a diffraction pattern in a resolution, 1 angstrom resolution, which is not the best, but still good enough to structure. With this data, the structure was solved, and it was found to be a 6-fold interpenetrated structure. Then the third example would be analyzing the API powder structure. Determine structure from crystal is by using crystallography. Crystallographic technology is a golden standard in pharmaceutical industry. But sometimes the pharmaceutical compounds doesn't grow into big crystal. This is a case. This compound, we only obtained a nanocrystal with this compound. It's like a rod-like crystal, and then we used micro-LED to collect diffraction data from this crystal and solve the structure. And this structure was delivered to our customer within 3 days. Co-crystallization is a technique. It's a technique that quite useful in drug solid state research, because co-crystallization can alter the solid state characteristics of the active ingredients without changing the structure. So the efficacy of the drug doesn't change, but maybe we can improve the stability. Sometimes we change the solubility for some purpose. So co-crystallization is a very useful technique in the drug solid state research. But one problem with this technique is that it's hard to get a large crystal, because you don't want to change the solution for growing the co-crystal. So there is very limited selection of solvent for you, and the structure of the co-crystal is quite crucial, because only with the structure you get information that those 2 ingredients are actually co-crystal co-crystal together rather than two of them crystallized separately and mixed physically. This information is also important for the drug to be proved by the authority. So with micro-ED technology, we can quite straightforwardly collect data and solve the structure of co-crystal, and it's very helpful for pharmaceutical companies. With micro-ED, we can also determine structure of each phase from a mixed phase sample. So we can, it's also quite straightforward. In the TEM, we just select the crystal, different crystal, and the solve structure separately. Then you would understand which particle is corresponding to which structure. So sometimes you would like to know if a minor phase is present in your sample. For example, in a pellet, you have only a few percent or even 0.1% of your active compound, and you would like to know, the authority would like to know if the compound is if the crystal, if the polymorph has changed during the formulation process. So normally, powder X-ray diffraction is used to determine the polymorph of a minor phase in a mixed sample, for example, in a pellet. But there is a limitation for powder X-ray diffraction. You can only determine the content as low, higher than a few percent, for example, 3% or sometimes 1% if your instrument is good enough. But with micro-ED, you can detect we have detected the minor phase which is contained as low as 0.1%, and maybe a lower content can also be detected, because you can screen all the particles in your sample and select anyone you are interested, and so determine the structure of that particle. So chirality, absolute structure, is another interesting topic for example, medicinal chemist. After then synthesis their target compound, they would really like to know the chirality of their compound. Normally, large crystal is needed to. Then they have to grow a large crystal to do single crystal X-ray diffraction to determine the absolute structure. But with micro-ED, we can detect the absolute structure from just a nano-sized crystal. This is one example. The absolute structure of this molecule is determined by micro-ED. If we how do we do this? We prepared two structures. One with each of those structure with one chirality, and we respond those two structures and compare the R value obtained from those two structures. And then we found that there is a significant difference between two different chirality. The one with significantly lower R value is the one with the correct chirality. We have also tested this method to more than 10, maybe 20 different molecules. here we have listed 1, 2, 3, 4, around 10 molecules. All of them has the right chirality showing lower R value. So this method is quite robust to determine the absolute configuration of the chiral molecule. This example is about to reduce the sample consumption. As I mentioned before, sample consumption is concerned by medicinal chemists as well as biologists, because their samples are quite precious. We combined the micro-ED technology as well as the mosquito crystallization robot. This robot can handle is like a nanoliter liquid handler. So so with this robot, we can lower the consumption of each experiment significantly. We only need nano. We can handle nanoliter solvent, and for each experiment, it consumes only, for example, microgram of samples. And then if we combine this method with micro-ED, we can also reduce the experiment that we perform to screen for screening the crystallization condition. Since we need only nanocrystal, so we don't need to screen so many crystallization conditions. Combining these two methods, we have one example. We got a nano-sized crystal with using only 12 milligram of samples and solved the crystal structure. This method, this technology is quite attractive for those scientists working on natural products, because each gram of their samples might take several weeks of their work. Okay. The last example will be about the structural biology. IL-5 alpha is an important drug target. Our collaborators first would like to solve the structure of this protein by using traditional X-ray diffraction, but it took them more than half a year. Then spent more than half a year to grow to try to grow a large crystal, but failed. Then within a couple of weeks, we have already we took a small crystal of this protein and milled into a lamina and collect the micro-ED data, and then solve the structure with a resolution of around 3 angstrom. We can already see the interaction of the ligand and the target protein. So within a couple of weeks, we have already got structure. So for micro-ED technology, there is also some challenges that we are still facing. For example, in some case, we have only low resolution data for those low crystalline material, and with this data we still don't have really good algorithm or method to solve the structure. And for many radiation sensitive sample, it is still an issue. Even though we have cryo holder and we have very sensitive detector, but still for some protein, they are too sensitive under the electron beam. And for large molecules, for example, polypeptide and some unknown protein, we still have the phase problem. So how to determine the phase for those to solve the structure of the large molecule is still a challenge for micro-ED. So thank you very much. This is all for my presentation.